Welcome to This Explainer. Look, if you're a focused learner who is ready to truly grasp how to think like a scientist, you are in the perfect place. Today, we're transitioning into the absolutely fascinating world of secondary science. And I promise you, this isn't just about memorizing some dusty facts from a textbook. It's really about upgrading how you perceive the entire universe. We're going to explore the ultimate toolkit of scientific inquiry, giving you the mental models to understand everything from a bouncing ball to the wildly complex physics of a burning star. Right out of the gate, let's talk about the ultimate toolkit. Think of two incredibly powerful symbols, a magnifying glass and a compass. The magnifying glass, that's your careful observation. It's that ability to look closely at intricate patterns and actually notice the subtle details that everyone else just walks right past. But observation by itself just isn't enough. That's where the compass comes in. The compass is your directed exploration. It guides your focus, helping you pick the right models and define the actual boundaries of what you're looking at. Keep these two tools in mind because they're going to guide everything we discuss today. Okay, let's dive into our roadmap for today. We're going to hit 1. Curiosity meets deep exploration. 2. The art of simplification. 3. Precision, math, and estimation. 4. Architecture of knowledge. 5. The power of prediction. And wrap up with 6. The interdisciplinary reality. Let's get into it. Section 1. Curiosity meets deep exploration. You know, science fundamentally starts with that natural, burning curiosity we all have about the world around us. It starts with just asking why or how. But I want you to notice the massive leap from primary to secondary science here. Primary science is that basic observation, noticing the intricate veins on a leaf or wondering why a rock falls to the ground. But secondary science, it completely upgrades this. We move into deep exploration. We start translating those basic visual observations into measurable symbols, into chemical structures, and into testable mathematical models. We are moving way beyond simply knowing what happens to rigorously proving how we know it. Moving right along to Section 2, the art of simplification. So the universe is ridiculously complex, right? When we're dealing with it, simplifying a problem is actually a deliberate strategy, not a mistake. Here's how it works. Step 1 is our observed reality. Imagine a car driving down a mountain road. It is full of complex details, the wind resistance, the heat of the engine, the specific friction of the tires. But if we just want to know how fast that car gets from point A to point B, all that extra detail is just noise. So in step 2, abstraction, we mentally strip away the environment. And finally, in step 3, we create our scientific model. We literally strip that car down to its most essential elements, a single dot on a graph with a vector arrow representing its velocity. By deliberately ignoring the irrelevant details, we can actually solve the problem. And this art of simplification, it works literally everywhere, no matter the scale. Take the microscale, a cricket shot. If you want to calculate the ball's trajectory, the model only cares about the mass, speed, and direction. Notice what it intentionally ignores: the brand of the bat, the color of the ball, or how long the grass is on the field. None of that matters to the math of gravity. Now contrast that with a macro scale. The famous physicist Meghnad Saha didn't try to model every single complex internal process of a massive star. By simply treating the star as a hot gas using the Saha equation, he successfully explained how a star's color is deeply connected to its temperature and pressure. Simplification is what actually unlocks understanding.
All right, Section 3, Precision, Math, and Estimation.
So, now that we've simplified our world into these neat models, we need the specific tools of rigor to measure it: standard units, equations, and the absolute crucial skill of making reasonable estimates. I want you to look at this very specific number, 22,300. Lock that in your head, because 22,300 is the exact amount of fuel, in kilograms, that a specific passenger airplane needed to safely make its flight to its destination.
But, well, things went horribly wrong. The flight needed 22,300 kilograms. However, the ground crew did all their calculations using pounds instead of kilograms. And since a pound is significantly lighter than a kilogram, that plane was loaded with vastly less fuel than it actually needed. It left them a terrifying 15,000 liters short in midair. It's a high-stakes anecdote for sure, but it brilliantly highlights why Standard International, or SI units, are universally critical. A kilogram has to mean the exact same thing everywhere, to everyone. It ensures fairness in trade and vital, life-saving safety and engineering.
Of course, once we have our precise units, we have to process them. And yes, that means math. But hey, if math gives you anxiety, let's reframe it real quick. Mathematics is simply a language for thinking. An equation like v equals d over t, velocity equals distance divided by time, isn't just some blind calculation tool you have to rote memorize. It is a highly compact, elegant statement about how physical reality actually relates to itself. Reasoning and understanding the physical situation absolutely must come before memorizing the letters.
Okay, here's a fun one. Sounds impossible to know how many liters of air you breathe in a single day without a fancy lab, right? Let's break it down using estimation. Step 1. Time. We take about 15 breaths a minute, which translates to roughly 20,000 breaths in a 24-hour day. Step 2. Volume. Think about blowing up a standard 2-liter party balloon. It takes about 4 to 5 breaths, so 1 breath is roughly half a liter. Step 3. Synthesis. Multiply those 20,000 breaths by 0.5 liters, and you get an amazingly reasonable estimate. You breathe about 10,000 liters of air a day. Estimation is like a superpower. It builds your intuition and helps you spot glaring errors instantly.
Which brings us to Section 4, the architecture of knowledge.
Once we gather all this precise, mathematically reasoned data, we have to formally organize it. And to do that, we need to bust a massive myth right now. You have definitely heard someone dismiss a big idea by saying, oh, whatever, that's just a theory. But in science, a theory is never just a guess. A scientific theory is an explanation of why patterns occur, and it is heavily built upon rigorous evidence and careful, repeated testing. It is the absolute highest level of scientific understanding, though importantly, it always remains open to improvement based on new evidence. Let's break this architecture down just a bit further into 3 main categories. First, you have a law. A law describes the what, a regular pattern observed in nature. Think of Newton's laws of motion, explaining that sudden jerk you feel when your bus stops. Next is the theory, which we just nailed down. It explains the why behind those patterns, like atomic theory explaining how molecules form. And finally, we have a principle. Principles are the broader, overarching ideas that help make sense of a situation, like the conservation of energy. Understanding this architecture is absolutely crucial for thinking clearly about any scientific claim.
Section 5, the power of prediction.
So, what is the ultimate test of all this structured knowledge? It's prediction. The true value of a scientific model or theory is how well it accurately predicts what is going to happen next. Now think about everyday guesswork. That's looking at some dark clouds and guessing it's going to rain. It's based on unreliable intuition and simple yes-no questions. Honestly, it's a dead end. But scientific testing? That's where we seek measurable evidence. We ask, what exactly is the humidity? Is the temperature dropping? What's the wind speed? By evaluating past patterns against current data, our confidence skyrockets because our reasoned predictions actually match our specific observations. And this predictive power, it is our absolute best weapon against misinformation. Take a look at this incredibly common viral claim. Food becomes harmful during a solar eclipse and shouldn't be eaten. How do we bust this myth? We use scientific questioning. We already know from our models that an eclipse is literally just a play of shadows as the moon blocks the sun. So we ask the basic physical questions. Does the temperature change enough to spoil the food? No. Is there a new chemical mechanism somehow introduced by a shadow? Definitely not. By just applying basic logic and physics, we easily completely disprove the claim. This actually leads us to a really beautiful realization. No scientific theory is final. Openness to being corrected by nature is what makes science uniquely reliable. The true strength of science isn't about knowing every single thing with absolute certainty. It's actually about possessing the intellectual humility and the rigorous framework required to reject your own ideas the exact moment new contradictory evidence arrives. Finally, Section 6, the interdisciplinary reality. You know, we might learn science in separate, cleanly divided classrooms, but nature does not care about those artificial boundaries at all. Take something as simple as a face mask. If you want to design an effective one, you can't just use one branch of science. You need physics to understand the electrostatic attraction capturing particles. You need chemistry to design those specialized polymer fibers. You absolutely need biology to understand the physical size and the actual behavior of the viruses you're trying to block. And you need mathematics to model the airflow and calculate the overall filtration efficiency. Solving real complex challenges means all these disciplines have to work together perfectly. And that brings us to a super vital point. Science is a profoundly human endeavor. It is driven by our curiosity, our creativity, and a massive amount of intense collaboration. It's this living, breathing system that grows across generations as people test ideas, share their results, and, inevitably, learn from their mistakes. But the most important takeaway is this. Even if you never put on a lab coat or become a professional scientist, this structured way of thinking is your ultimate tool for evaluating information critically in our hyper-technology-driven world. So as we wrap up this explainer, I really want to leave you with a provocative question to chew on. How will you apply the magnifying glass of evidence to your own life tomorrow? The next time you see a crazy viral headline or you face a really complex problem, are you going to rely on everyday guesswork, or will you break it down, estimate, model, and demand the evidence? Transitioning into secondary science, it is really just the beginning of an amazing lifelong journey. I encourage you to always look carefully through that magnifying glass of evidence and let yourself be guided by the compass of curiosity. The universe is literally out there waiting to be understood. Thank you so much for joining me for this explainer, and hey, happy exploring!